You can go read about some of the work we did in spam fighting if anyone's interested. I'm not here really to talk about spam fighting necessarily. It's emblematic of the things I want to talk about, and nothing here will be specific to spam fighting, but we'll just use it because it's fun and it motivates a bunch of these examples. One of my rules here is you got to get in trouble like in the first 3 minutes, so let's try quickly. I spent a lot of time in infra, and I watched a lot of teams working on different things. Data sort of infra people and teams, and ML infra and teams have done a bad job communicating with one another. I'll just say it. I've seen a lot of data infra that's really good at being data tools, really bad for serving ML for various reasons. We could talk about it to some degree. I've also seen ML teams really underappreciate how much infra they need to run an ML app in production. And pretty much the worst mistake you can make is to sort of not realize you're building a database as an ML team. Like, oh, whoops, I'm accidentally building a database. I thought it was a feature store. It turns out it's an entire database I need to build, for example. This conversation is actually really happening, emerging as we speak. I don't want to make it sound like it's just happening. Last few years, at least. So you see it in at least 3 predominant places. Feature stores have started to become a grown-up piece of infrastructure, kind of in the open source world. Vector databases, a very hot topic, which we will spend a decent amount of time on here in a bit. And these kind of orchestration layers, right? So things that treat, for example, the life cycle of a feature as a first-class citizen. All of these are places where the data tools in the data world and the ML tools in the ML world are actually collaborating in a good, healthy way. So, okay, ostensibly this talk is about the intersection of domains. Let's just talk about these domains so we're all on the same page super briefly. First is this real-time data world of search and analytics. This is where Rockset lives. This is our bubble. I will take just a second to explain to you what I mean by real-time. Real-time is one of these words that people use, buzzwords that may or may not have a meaning depending on what room we're in. Effectively, it means usually both of these things are necessary for your app. You care about the query latency for your data, and you care about the data latency of your data. Queries, I think most people understand. I want fast queries, right? But data latency may be a little bit, I was warned there might be flickering, so I can only do so much, though. Data latency might be the one that's a little more subtle. Basically, the idea is as soon as a piece of data is created, how long until it's ingested and queryable, right? That is the fundamental of data latency, and it often determines how real-time an application is, right? If you need last seconds data versus last minutes data versus last maybe milliseconds data, these are all different generations of real-timeness. I will give you guys some super important trade secrets if you don't happen to work in the database world. If you need query latency in a database, it means you need indexes on your data. Top secret, don't tell anyone. Don't record this and put it on the internet. Data latency is a little trickier, right? So data latency is really about having these indexes be updatable in a streaming and sort of incremental fashion, right? You can't rebuild your database from scratch, your index from scratch constantly if you want it to be real time. And if you know anything about vectors, this will come back soon. There is this other giant bubble, the AI and ML infra world. AI people want to train models, they want to serve models, they want to do all the other things associated with managing the life cycle of these models. Not all of that is real time. So for example, training in the ML world is typically not a real time operation, it's typically more of a batch style operation. But a lot of the serving stack within AI and ML apps is a real time application. So these are the 2 domains I want to collide. This is what I want to talk about today. I'm going to use spam fighting as my motivating set of examples. I said before, for fun. Nothing here is specifically spam fighting talking. This could be anything. Realistically, we could talk about product recommendations on Amazon. We could talk about Twitch streams that you want to go watch instead of this talk. Anyway, okay, so yes, what we're going to do is observations from the middle. And I had this original agenda. Like if you actually read the abstract, this is roughly kind of what it said. I made a realization while I was working on these slides. This is too much. This is too much content. This would take 2 hours. No one would sit here for 2 hours. And so I actually wanted to focus on one thing, which is super topical, is very much in this intersection, and is emblematic of effectively everything. So I'm actually going to talk today specifically about one set of really important topical challenges, which is about vector search in this intersection, specifically real-time vector search, when there's a real-time component to your vector search applications. So again, it's emblematic, right? So it touches on most of the things I was going to talk about anyway. And so we're going to talk about vectors for the most of today's talk. But first, let's talk about spam fighting infra, just to give you a sense of just to make sure we're all on the same page about what spam fighting infra is, why it's a machine learning app, and so forth. Spam fighting is a pathologically real-time problem. It is an adversarial situation, right? Users are uploading things all the time. And so I need data as fresh as possible all the time. So if I want to answer the question, how many comments have you made in the last minute, it shouldn't take me like 3 minutes to know that you sent 1,000 messages in the last minute. That's catastrophic from a spam fighting situation, right? I guarantee you will get spam in exactly those bursts if you can't detect it quick enough. So data latency is paramount in spam fighting. So that's the first checkbox in the real-time thing. Query latency is also really important in spam fighting. Some people naively might think that you can sort of asynchronously clean up spam. In other words, let the user post their comments, I'll classify it and clean it up later. This turns out to not work very well. It's actually quite bad, and it's for two reasons. One is that the first reason is that spam does most of its damage soon, so you actually don't want it there at all, even if you're going to clean it up eventually. Second, I don't want to write amplify spammers. I don't want to give them two writes to my database, right? Once to write, once to clean up. That's the wrong cohort of users to write amplify. These are spammers. So fundamentally, you want your spam protection synchronous. You don't get to write to the database until I think it's not spam. That means that my latency of my queries, my classifications, is part of the product experience. It's in the critical path of my product. My site will not feel snappy if it takes me 10 seconds to decide if it's spam or not. So I've just given you the two pillars of real time. That is, spam fighting infra is a deeply real-time problem. Certainly not the only one. There is one other really interesting thing in spam fighting, that approximation is okay in spam fighting. If you're going to give me a 99% correct, accurate answer, but 10 times faster, I will take it every single time in spam fighting. This is true of almost all kind of ML recommendation style systems. And if you know anything about vectors, this will come back with a vengeance. Approximation is crucial in the vector world as well. And so this is a little bit of foreshadowing here. So, all right, let's talk about vectors and spam fighting. So vectors were very powerful in spam fighting, and they have been for a really long time. We were doing vectors before they were cool. They're cool now, but even before they were cool, they were popular in the spam world. There's this classic question, is this photo that you're uploading me spam? This is a very hard question historically to answer. Traditionally, people would try to solve this with like a point classification. I'm giving you an image, I know who uploaded that image, I know some metadata about the upload, I know the pixels in the image. Can you look at that and tell me if it's spam or not? Can you train a classifier to tell me if that image is spam or not? Historically speaking, the answer is absolutely no. That classifier cannot be built, it will not work. It's possible that that's changing literally as we speak. I've heard rumors that some of this AI revolution might actually have made progress on this question. I am skeptical, but I would be happy to be wrong. I would love to be wrong if we've made non-trivial progress here. So vectors enter the equation. I don't actually know how much background to assume for people about how much you know about this whole vector thing that's going on. I'm going to do really quick 101 just in case. The basic idea is you take really unstructured data. In our example, it's an image. You're going to embed it into a vector space via machine learning, AI, right? So that you train this big old AI, it projects this into a vector space. And the idea being that distance in this vector space preserves some semantic you care about, okay? So your ML model is trained to preserve this semantic. So distance measurements is a sort of a precise notion of some notion of likeness. Okay, and in our case, photos being alike. That's the basic idea. So going back now, our image problem becomes very different when I introduce this vector concept. What I tend to do is find and link photos based on their similarity, which is to say their nearness in this vector space. And as soon as I have that little bit of fan out, things change radically. And this actually powers a significant fraction, or at least one time powered a significant fraction of like image-based spam fighting. For example, how many photos look like this photo? If the answer is very few, it's almost certainly not spam. If this is the first time I've seen a photo, it's almost certainly not spam. Maybe even more powerfully is to start to fan out beyond just the photos. So of all the users who uploaded photos that look like this, how organic is that set? If 1,000 people uploaded a photo and all 1,000 of them were registered during the same 1-hour period in September, that's not probably kosher, right? And once you have this idea, you start to think in terms of clusters of data, not in terms of any particular point of data, right? So does this cluster look good or not, right? That's the transformation that gets made as soon as you have vectors and this notion of nearness in an image space. And so we could talk about this all at great length, but it's basically this idea of clustering. Once I have clusters of photos, I can start building classifiers on clusters of photos. I can also just have humans annotating. That actually becomes a scalable thing to say, this entire cluster of photos is no good. Don't allow them on the site, for example. And the important thing is the real-time component of this has now been reduced to exactly 2 steps. Step 1 is to embed this in a vector space, so create a vector from your image. Step 2 is figure out what cluster, if any, does it belong to, and what have I labeled that cluster, right? Is it good or bad? So my online real-time component is exactly vector generation, vector search, right? So I can power a lot of spam fighting with vector search, right? So hopefully that motivates where we've headed, which is to say vector search in real time can power a wide range of ML apps. And again, not to belabor the point, this isn't just spam fighting. I want to make a comment here really quickly, since there's been a lot of talks about LLMs and all these other things. Vector search is a feature of vector databases. It would be a grave error to confuse these 2 things. So a vector database is a database, and databases are a non-trivial category of pieces of software. Obviously, vector databases store vectors, and they can do vector search, but they do a lot more than vector search. And I will make a controversial claim. I've actually been making variations of this claim with different people, and I don't think it's actually as controversial as I thought originally. But a good vector database is more database than vector. It's going to have vector stuff in it. There's going to be vector technology there, but the database part is non-trivial. Like everybody remembers like that senior level class, maybe grad level class, there was literally a database textbook that was like this thick. That database textbook hasn't gone anywhere. If you want to build a vector database, you still have that entire textbook and all the problems it's laid out to deal with. And so it's not to say that vector search is an easy problem. In fact, we're going to describe why it's hard. That's literally all the rest of the slides. But it joins a whole host of well-known hard database problems. And so my one takeaway, if anything, is to be wary of the enterprising engineer that wants to download a vector search library and productionize it. That is the very first step on inventing your own database accidentally. You can do that if you want. You can build your own database if you want. Just do it consciously. Don't do it accidentally. That's my only plea. Let's talk about indexing vector data. So in a traditional database sense, you need indexes. Vectors are a really hard thing to index. As a general rule, you can't index vectors. To be more precise, low-dimensional vectors are indexable in a traditional sense. This has been done for a long time. Lots of databases have them. So for example, things like geospatial or latitude, longitude are low-dimensional vectors. You can use these kinds of space partitioning algorithms. That's what's over here on the right, by the way, space partitioning type of algorithm to build an index that lets you quickly look up nearest neighbors in a traditional sense. In high dimensionality data, there's a thing called the curse of dimensionality, which essentially means you can't do better than linear scan. You basically have to look at every point. If you take a 1,500 dimensional vector, you throw it in a KD tree to try to search it quickly, it will still scan all 1,500. Excuse me, it will still scan all the vectors in the database. This is what the idea of the curse of dimensionality is. And just to underline the point, this whole vector AI thing that's going on out in the world right now is all in high dimensions, right? So OpenAI's text model is 1,500 dimensions. It is very much in the high dimensional category, which basically means these vectors are not indexable. That's what it means, at least in a traditional sense. So this enters into these approximate indexes. So hopefully, some of you have some background here, but if not, we have to give up the idea of having exact nearest neighbors. We have to give up the idea of an exact index in the traditional database sense, and we have to kind of bring approximate indexes into the equation. Approximate indexes are not a thing in a traditional database, typically. Like that's not really a thing we've done very often. But it's necessary for vector search. This is a super active area of research. You've probably heard some of these things. You know, HNSW is a popular thing nowadays. I'm not going to cover this stuff right here. This is literally like conferences are happening, papers are being written, PhDs are being given on this topic of how to more efficiently find vectors in a vector space in an approximate fashion. But I will say that ANN is not a silver bullet. So even if I grant you've built the world's greatest vector lookup algorithm, it's super efficient with minimal accuracy trade-offs, it preserves a sort of logarithmic style lookup instead of a linear scan, you've only solved the first hard problem. Even if I grant it to you, it's a hard problem in and of itself, you've only solved the first hard problem. And there are a whole lot of really hard problems on its tail that you probably didn't think about when you were thinking about building a vector application. And this is what I actually want to talk about. So even if I grant you the first really hard problem, the one that gives PhDs, you still have lots of hard problems in your future. And that's the rest of today's talk. So the hard problems in vector search, not including the first one, which is actually building a good vector search algorithm. I want to stress something here. These are hard problems. I don't exactly know what hard means, but in this case, these are not solved, to be clear. We haven't solved them. We're working on solving them, but do not trust anyone who's told you anything I'm about to tell you is a solved problem. Many more papers will be written, many more PhDs will be given on everything involving all of the next slides. So if you want a PhD, I have some ideas. So problem number one in vector search is incremental indexing. So great, you've built the world's greatest graph-based hierarchical navigable small worlds data structure. It has all the vectors in it. Everything is awesome. You can find vectors instantly. The problem is, can I add new vectors to this thing? How do I add new vectors to this thing? This is fundamental to the data latency question, right? If your use case requires that new things be added and findable in your search, data latency is the thing you care about, you have ran into a very hard problem in vector databases. An enterprising engineer might say, hey, I can imagine naively inserting things into this data structure, and that'll work probably, maybe. As a general rule, this doesn't work well. And the mental model for most of these algorithms is like a balanced binary search tree, right? You do a lot of work to make your search tree balanced, and then if you start inserting random things into it, it becomes unbalanced. And as a general rule, these kinds of ANN algorithms deteriorate even faster than a balanced binary search tree would deteriorate in terms of speed and accuracy trade-offs. So as a general rule, naive insertion doesn't work very well. They're hostile to some degree to incrementally updating these vector search things. Now, again, lots of people have ideas. Lots of things are happening in this space. Lots of people are trying to solve this problem. Some of the options include, one, you can just embrace this suboptimal incremental indexing. You say, look, I'm going to insert naively into this thing. I know my index is going to get worse. I'm just going to rebuild it periodically. Periodically rebuild my index from scratch, swap it in. That's how I'll build the system and productionize it. A database person gets instantly very, very uncomfortable with this idea, because this idea of like rebuilding my index from scratch periodically immediately is horrifying. Like, where are you going to do that? Are you going to do that on my database? Like, while I'm serving queries, you're going to kick off like a 3-hour CPU-bound job of reorganizing all the vectors? That seems horrible. Maybe you'll put it somewhere else, and now I have consistency questions. Like, what's the consistency model of this? How is that going to work? How are you going to shard this thing? Like, I don't understand how you're going to do any of this work. But you can go down this road. It's just not an easy one. You can embrace a more batch index style. So the idea is you accrue new vectors as they come in, and when there's enough of them, you build an index of just those, and you sort of keep a history, so to speak, going backwards of snapshots of things. You can occasionally even compact them So again, if you know anything about databases and how databases have been built over time, this is an extremely common strategy called a log structured merge. It's actually the basis of software like RocksDB and other things. This is one of the probably ways most people will be doing it in some form. It also has its problems, though, because it's not the most real-time setup in the world. There's problems with kind of more recent vectors being fundamentally inefficient to search. There is a third option, of course, is you could just improve these algorithms, right? Like if you come up with a better algorithm that does really great vector search, but also is elegantly, incrementally updatable, like congratulations, like you can have your PhD and write your papers and publish it, and I will happily implement it. Lots of people are working on this, of course. I think we'll make incremental progress on this, but I don't know that we'll have like a revolution here. I think this is going to be a hard problem that we're going to have to solve one way or the other. Yeah, going forward. So yeah, hard problem number 2. This is called metadata filtering. So this is one of these problems that, depending on what world you live in, has different names. So if you're in the AI or ML world, this is often called metadata filtering. Sometimes it's called hybrid search, but hybrid is a bit of an overloaded term here as well. If you're in the data world, this is like the where clause of your query. Like literally, it's the where clause. Here's my example using the spam fighting motivation. Like show me all the images like this one, which is a vector lookup. That's a vector search, that were uploaded in the last 10 minutes. That is a metadata filter. And in this case, it would be like a SQL query, right? Like where the upload time was less than 10 minutes, et cetera, et cetera. This is a super hard problem in vector search. And I would go one step farther, maybe make a slightly controversial claim again. It's also not optional. I would argue that just about any good vector use case, any good app will be made better by having some fraction of metadata filtering, like some boundaries under which you're removing the set of data you're looking at to make the user experience better. It might not be obvious why this is hard if you haven't spent time thinking about this. So I'll try to do that problem justice here. I mean, the basic idea is this index is this like typically this graph-based hierarchical thing that's pre-computed on all the data. So if your filter slices that data weirdly, you don't have an index of the filtered data. You only have a filter of the index of the unfiltered data. So the index and the filter might really compete with each other at how to best sort of find data in this space. Again, our enterprising engineers have many solutions to this problem. The most obvious solution is what was typically called post-filtering, which is to just overfetch, essentially. Like, hey, vector index, give me the 1,000 closest vectors. I'll filter after the fact and hope I end up with the amount I wanted to start with. Like, let's say I want 100. I'll fetch 1,000, I'll apply my filter, and with any luck, I'll end up with 100. This works obviously pretty well if it's not too selective, but if it is, it won't work very well. Pre-filtering is this idea of filter first and then just scan your results. So this essentially throws out the index. The index doesn't do any good here. So if you just apply your filter, see how many vectors meet your filter, and then just scan them all, that works, that will totally work, but your index has not participated in this process. And then the final option is you can somehow build an ANN search algorithm that includes some form of metadata filtering in the process of doing it. This is, again, another area where papers can get written, and it's a pretty active area of research. So again, if you want to write more papers, down here, help me. And this leads finally to hard problem number 3, which is hidden in hard problem number 2. If you understood this idea of pre-filtering and post-filtering, sometimes pre-filtering is a good idea, and sometimes post-filtering is a good idea, and the choice of when those are good has to do with the selectivity of your filter. Okay, so what does that mean? So in the database world, this is a very common and long-standing problem. If I say, give me the 5 nearest neighbors where X is a filter, the correct way to evaluate this often depends on how selective X is as a filter. So if X is not that selective, meaning let's say it only wipes out half the candidates, then post-filtering works super great. So post-filtering, remember, is this idea of overfetch. If I want to find 5 nearest neighbors that meet this filter, I'll fetch 20. I'll apply my filter, which on average wipes out half, and almost always I'll get the 5 that I want at the end, no problem. On the other hand, if X is extremely selective, this doesn't work at all. The pre-filter technique actually works much better. So pre-filter is like, hey, I have this really stringent metadata filter where the color is red and it's over $200 and it was built on a Tuesday. It turns out there's only 5 rows in my database that meet this criteria, in which case I can just pull all 5 rows and rank those by distance. I don't need an index to do that lookup. So the idea of how best to execute the same query is a function of how selective the filter is. This is one of those problems that if you've taken all the database classes, there's just like a whole thing you learn about. And there's like mountains of technology built into all your favorite databases to track predicate selectivities and use that in what's called a cost-based optimizer. If you don't know that and you wander into this space by trying to bolt on like metadata filter onto like a vector database, this is one of these giant pieces of technology that you end up accidentally reinventing. And you'll spend a decade probably realizing it. So anyway, going back to the database perspective, cost-based optimizer is the thing we've had for a long time. It's not actually that hard to plug a vector search into it to optimize it based on this selectivity to kind of do this pre-filter versus post-filter thing automatically in your database. But of course, the hard part here was having the cost-based optimizer in the first place. That's actually the hard part here. All right, so I've given you 3 hard problems in vector search when vector search needs to be done online and in real time. So they were, just to recap, incremental indexing, so adding new vectors to this thing. Oh, by the way, we didn't talk about mutating or erasing vectors. That's even harder. So just adding vectors is itself a hard enough problem. Metadata filtering, which I consider to be non-optional and super important. And then optimizing these metadata queries becomes really important. This whole idea of selectivity optimizations becomes really hard. So anyway, that's my talk for today. I have a couple things that I kind of could wax philosophically about. Maybe if you find me outside, I will. I think at the heart of it, it's like watching these 2 groups of people slowly work together. I just don't want you to build your own database by accident. You can build it on purpose. By all means, build your own database. Do it on purpose. But on the flip side, if you're a data person, don't underestimate how hard your data tools are to use for ML use cases. If you go talk to ML people about how they want their data tools to work, there's a lot of gaps. So for example, the idea of an approximate index in a database is like a crazy idea for data people. Like, what? What are you talking about? Turns out it's super valuable for an ML style workload, like in this case. And there are really, really hard problems. Like I granted you an entire database. I granted you the vector search problem, and I still can come up with 3 or 4 ways that this becomes a nightmare for your application. So there are a lot of hard problems in this space. So it's a fairly exciting space, a lot of problems to be solved. And that is my talk. So thank you.